So hello everyone and welcome back to the Mid-Atlantic Micro-Nano Alliance's virtual seminar series. I'm Heidi Leonard, president of MAMNA. Today we're in my kitchen, but today we're also joined by Alexis Payne, who will be discussing her recent work producing and characterizing high energy density capacitors for energy storage applications by conformally coating metal foams with antiferroelectric thin films. So Alexis Payne is a doctoral student in material science and engineering at North Carolina State University under the advisement of Professor Jacob L. Jones. And she's also a Journeyman Fellow in the Energy and Biotechnology Division of the Army Research Lab in Adelphi, Maryland. Prior to starting her doctoral program, she obtained her BS in physics from the College of Charleston and worked at Northrop Grumman Synoptics as a research and development optical engineer. This is really impressive. And now here's Alexis, and I'm excited to hear what she presents.
Hello, everyone. As I was so wonderfully introduced by Heidi, my name is Alexis Payne, and today I'm going to be presenting atomic layer dielectrics on metal foams for energy storage. I am a doctoral student at North Carolina State University studying material science and engineering, and I have the privilege of conducting my research at the Army Research Lab in Adelphi, Maryland. So to give you an idea of the flow of this talk, I'm first going to give you a lot of background information before I state the goals of this research, and then give you the details of the research that we conducted. So to start, energy storage is going to be something that continues to be needed as energy demands globally continue to rise. More and more people will get on the grid. We'll have more and more devices in our pockets and in our homes, thanks to the Internet of Things. So with that demand in energy increasing, there'll be an increasing demand for energy storage as well. Now, if I were to ask you what we use for energy storage, many of you would respond with batteries, and that's a great answer. Batteries are made up of a cathode, an anode, and an electrolyte in between those. The electrolyte chemically reacts with the cathode and anode to store energy through chemical bonds. And because you're relying on a chemical reaction, it's kind of slow, and we've all experienced that battery that's slow to charge as much as it's really energy dense. And it also has a low power output because of that as well. So in the plot on the right, they're in the bottom right-hand corner. Now there's another device we use for energy storage that you may not be as familiar with, known as a capacitor. And a capacitor is made up of an electrode, a dielectric, and an electrode. And if you don't know what a dielectric is, that's totally okay. I'm going to be going over that in a minute. However, capacitors are great in that they store energy as static charge, and they just rely on electrons moving, so they can be charged really rapidly. They can therefore have a really high power output as much as they aren't as energy dense as a battery, and therefore they're in the upper left-hand corner of the plot on the right. Their applications are many. You can find them in regenerative braking systems. You can find them in audio amplifiers. You can also find them in any application you want a really large pulse of power quickly, such as a defibrillator. Other places you find capacitors in use in our technologies is in the circuitry of our electronics. They're used as passive components in things such as high pass and low pass filters. So like I said before, I was going to elaborate a bit more on capacitors and specifically dielectrics. Capacitors, again, are made up of an electrode, a dielectric, and an electrode. And a dielectric is simply an electrically insulating material that becomes polarized in response to an applied electric field. So when you look at this dielectric material, you can see that it has a bunch of molecules and they all have dipole moments, and they're oriented in really random directions. But when we go and apply an electric field, you can see with these pluses and minuses, we're applying an electric field, those dipole moments orient in response to that applied electric field. We say this dielectric is polarized. Now, when we think of dielectrics as a giant class of materials, it actually has many subclasses too. You can see this in the figure on the right. So A subclass of dielectric materials are piezoelectric materials, which polarize in response to a mechanical stress. There's pyroelectric materials, which polarize in response to a change in temperature. And then there's ferroelectric materials, which polarize in response to an electric field. But they're more unique than dielectrics in that you could remove this electric field. You can see on the left, the plus and minuses. If you took them away, the orientation of those dipole moments would remain, which makes it specifically a ferroelectric. Now, when thinking about ferroelectrics in terms of energy storage, we often look at the polarization electric field loops. And in front of you, you can see a 3-panel of polarization versus electric field loops. In the left-hand one, you can see a linear dielectric, in the middle, a ferroelectric, and the right-hand side, an antiferroelectric. So for the linear dielectric, you can see that as we increase the electric field being applied, we get an increase in the polarization. So as the electric field is being applied, more and more of those dipole moments orient in response to that electric field. Ferroelectrics, again, as you increase the electric field, you get an increase in the polarization till you reach the max polarization, P max. But as you take this electric field away, you come back to the remnant polarization. So no electric fields being applied, but you still have polarization. And then on the far right, we have our antiferroelectric. And it's characterized by a polarization electric field loop that has a remnant polarization of 0, but still is a really high max polarization. When thinking of these three in terms of energy storage, we have to go to the equation for energy storage density, which can be found in the bottom center of this slide. It is denoted by the green region in each of these plots. So more green is good. It's a higher energy storage density. The red region in each of these plots is energy lost. So more red is bad. Hopefully you'd agree with me if I asked you which of these you would use for energy storage. You'd also pick the antiferroelectric. And that's because it has a max polarization much higher than that of a linear dielectric, but it's not nearly as lossy as that of a ferroelectric. So now that I've given you all that background information, the goals of my particular research. So the goals of our research is to produce a functioning capacitor whose bottom electrode is a metal foam, and it is then coated with an antiferroelectric thin film, which is then coated with a top electrode of platinum. We believe that this novel architecture will enhance electrical properties over current state-of-the-art capacitors with a higher volumetric capacitance, with a greater temperature stability, and with lower losses. So in working towards accomplishing this goal, we first decided what antiferroelectric thin film we'd be using. So we decided on ferroelectric hafnia. And bulk hafnia is not known to be ferroelectric, and thin film hafnia was only discovered to be ferroelectric in 2011. And that was really exciting for all of us in this field, as most commercial ferroelectric materials, the two main ones, were found in World War II. Another great reason that we picked hafnia is it's compatible with current manufacturing methods. So hafnia is already in use in our circuits of our electronics as a gate dielectric. So when thinking about bringing this product to market, it has a much lower barrier to overcome to go R&D to commercial than other materials, as the technology is already there. It just have to be transitioned, instead of using it as a gate dielectric, to use it as the dielectric medium for a capacitor. Other properties that affect the electrical response of hafnia, besides going from bulk to thin film form, are dopants, what dopants you use, and how much of that dopant you use. In the panel in the bottom here, you can see that it's increasing dopant concentration of zirconia. And as you increase the dopant concentration, you can go from a linear dielectric-like response all the way to a classic ferroelectric response, all the way to an antiferroelectric-like response. And our materials, we use alumina. Alumina is our dopant for hafnia thin films. So now that I've introduced what our thin film material is, I'll now tell you how we grow it. So We grow our thin films via atomic layer deposition, which is also known as ALD. And ALD is a chemical gas phase thin film deposition method based on sequential self-saturating surface reactions. So 2 or more precursors, each containing different elements of the material being deposited. In our case, our precursors contain aluminum, and then another one contains hafnia. These precursors are let into the growth chamber one at a time. And when they're let in, they saturate the surface, forming a monolayer of material. And the benefit of only growing one monolayer at a time is that you can coat really complex structures, high aspect ratio complex structures, such as our metalphones, which you can't do with other thin film deposition techniques. So to understand how we dope our thin films, you can look at this figure in the bottom right, and that we'd grow a monolayer of hafnia by putting a pulse of hafnia in the ALD chamber, then have another pulse of hafnia into the ALD chamber, followed by a pulse of alumina to grow a monolayer of alumina. And this would continue, go on, so on and so forth. In this case, you can see that there's 8 layers, and out of those 8 layers, 2 of them are alumina, making this example film 25% doped, aluminum doped hafnia. That's a really high doping concentration compared to what we use. We use a doping concentration ranging from 4 to 8%, and our thin films are either 20 or 50 nanometers thick. So to start this work, we first decided to grow our thin films on a planar surface, and we used platinum electrodes. And the electrical characterization of the planar films can be seen in this slide. So on the left, you can see we have a polarization versus electric field loop. And you can see that the 4 and 5% here have higher max polarization values than that of the 8%. But the 8% has a much thinner, slimmer loop than that of the 4 and 5%. When thinking of this through the energy storage density viewpoint, you have to remember this plot I showed you at the beginning, where the green is the energy storage density that's stored, energy stored, and the red is the energy lost. So you can see that in our calculations here of the ESD and efficiency at increasing fields, that for the 4 and 5%, the dashed lines, the efficiency, you can see a drastic decrease in the efficiency with increasing electric field. And that can be seen with the wider loops. We can see we get down to efficiencies of 60%, as compared to the 8%, which maintain their efficiency all the way through high electric fields, maintaining it above 80%. Now, this is one way of looking at these thin films, but in reality, for thinking about using them in a device, you have to consider the operating voltage. Now, the operating voltage is typically 4 to 5 times lower than the breakdown voltage. So as much as we can look at them at the extremes, you would never run your device at those extremes, as you would experience breakdown rapidly. So you always back down from that extreme value. And that's why the operating voltage is significantly lower than that of the breakdown voltage. So this table shows you your breakdown field, which is reported per unit thickness. So as you can see, if we increase the thickness, because breakdown fields per unit thickness, we actually get an increase in your breakdown voltage. So your 50 nanometers have much higher breakdown voltages than that of your 20 nanometer thin films. And that shows up obviously in the operating voltage. The 50 nanometers can be run at a higher operating voltage. So this is the energy storage values and efficiency at that operating voltage. So here there is a clear winner. It is the 8% aluminum doped hafnia that is 50 nanometers thick. That gives you the highest energy storage density at its operating voltage. So now that we picked the thin film and the composition and the thickness that we were planning on using, we wanted to move on to growing our thin films on more complex structures. Now, why would we want to do that? So the big reason is because capacitance and area are related. You can see that in the equation here. As you increase the surface area, you increase the capacitance. So this isn't a new idea. You can see trench capacitors in commercial products. And that means that you're coating a higher surface area under the electrode for the same footprint, yielding a higher capacitance for the same footprint. And this has been done with hafnia thin films, as you can see in this panel. However, when you're thinking about actually using these, let's say for a pulse power application, you come into a problem, and that's your electrodes are really thin. They're 20 nanometers thick. That is current limiting. As you try and push a lot of power output fast, meaning you're trying to push a lot of current fast, you can't. It just is a non-starter for a device. So this is why we consider using and approaching this problem from a different angle and using metal foams. So we want to use metal foams as our bottom electrode because, first of all, they're 20 microns thick versus 20 nanometers thick everywhere. They're true metal, so they have both high electrical conductivity and high thermal conductivity. They have high surface area. They're commercially available and relatively inexpensive. Specifically, we use nickel, which is definitely cheap, or isotropic. So there's lots of different reasons why we'd want to use the metal foams. But again, we won't be current limited because we're dealing with a much thicker electrode base. So we have started work on this by depositing aluminum doped hafnia onto nickel. On the left, you see a polarization electric field loop of aluminum doped hafnia on planar nickel. It is 20 nanometers thick and 8% doped. And you can see we're having a linear dielectric-like response with an interesting hump here, which we believe is due to charge build at the electrode, one of the electrode interfaces. And we've also started depositions onto the metal foams themselves. Here you can see an uncoated sample, which is very silvery. And then you can see all these have gone through at least a ALD growth run. And you can see that from their color change from the uncoated. They just have gone through various processing conditions. So we haven't gotten a polarization electric field loop yet off of a metal foam itself that's been coated, but that's due to COVID. Thank you, COVID. We're still really excited about this though. So in summary, antiferroelectrics could support next generation energy storage devices. And by controlling our doping concentration and film thickness, we can optimize for the properties that matter at the operating voltage. And as much as we've deposited aluminum doped hafnia on foams, our next step is hopefully to measure successfully an antiferroelectric loop from the hafnia thin films deposited on the foams. We still believe that metal foams are going to be an innovative new capacitor design that could lead to better energy storage devices. So with that, I'd like to acknowledge everyone that I work with, both at ARL and at NC State. I also would like to acknowledge my funding sources. And with that, thank you for your attention. Any questions?
Thank you. That was a really interesting talk. And we have a couple questions. So the first one is from Siegel 7825. Is this a high temperature dielectric study? And Siegel withdrew his question, but never mind.
So I would just say that a lot of the highest temperature commercial capacitors that are out there today are rated for 230 degrees C. And that's like a nice high end, can withstand high temperatures. Tantalum capacitor, which is what we would be compared to in industry. And because of the Curie temperature of hafnia being around 400 degrees C, we think that, and nickel's melting temperature also being really high, we think that we can surpass what's commercially available now.
Makes sense. So Ryan's asking, from the slide about the operating voltage, increasing the percentage of alumina hafnia as well as the thickness seemed to keep improving performance. Is there a limit to this, or is there a Goldilocks scenario?
So that's a great question, Ryan. And there is a limit. And the reason why is capacitance is related to area. And if I go back to that slide, you can see this equation. So as much as increasing your surface area increases your capacitance, as you increase your film thickness, you get a decrease in your capacitance. So there is at some points where you grow so thick, you're being a detriment to yourself. And also at some point, your dopant won't form a homogeneous thin film, and that'll probably lead to not great electrical properties. So you don't want to keep increasing the dopant concentration indefinitely.
Right. I guess along with that question, Brendan is asking, what's the ideal composition and how would you choose?
So the ideal composition is determined by looking at how these thin films operate at their operating voltage. You just don't want to pick the film that can withstand the highest field or just look at one specific property. You always have to go back to how is this functioning at the actual operating voltage it would be used at, and what has the greatest efficiency and what has the greatest energy storage density. And we haven't done a complete study of all the doping concentrations and thicknesses yet, but from the ones we studied, we believe that the 8% aluminum doped hafnia at 50 nanometers is the best.
And Walter Smith is asking, can you clarify the advantages of these over supercapacitors, or is this a new kind of supercapacitor?
So this isn't a supercapacitor, and supercapacitors, I'll go back, sorry. If you're looking at this beginning plot here, that they try and balance both energy density and power density and live in this realm of 10 to the first to 10 to the fourth and 10 to the first and 10 to the fourth in joules per kilogram and watts per kilogram. Our thin film capacitors aim to increase specifically the energy storage density of a thin film capacitor. So we still want really high power output with the applications we're considering. And we just want to scooch this box to the right here graphically. So its advantages over supercapacitors that we're going to have still a much higher power density, but we hope that we can start getting energy density values that are comparable to something that you'd see in a supercapacitor.
From Griffin Fields, how does the nickel foam capacitor compare to conventional batteries in terms of energy density / power density?
Yeah, so again, going back to this plot, batteries are going to look super energy dense compared to our foams, but batteries are going to have nothing in terms of power output and compared to our foams. And that's just how it works, because the batteries rely on those chemical reactions. They're going to be more energy dense, but they're going to be much slower compared to our capacitors.
Okay, so personally, I have a question. So I really like porous material. So I think the metal foams are intriguing because I've never seen these before. But how do you measure the porosity of these foams and how do you know the surface area of them?
Yeah, great question. Okay, so the surface area we left out, we don't have to calculate it, and that it's a spec on the spec sheet that you get when you order the foams, since they're so commercially available and made. But in terms of when we do our electrical characterization, we know the polarization, what it should be per unit area for just on a planar surface. So we can calculate how much surface area is actually contributing to our polarization when we measure it on the metal foam and do a direct calculation there to show how much surface enhancement has gone into planar versus this nickel foam. And also, we haven't explored it, but you can buy nickel foams at a variety of porosities. So that is something that we can explore in the future. It's denser or wider or bigger just by ordering different types.
Right. I wonder if the different porosities, you end up depositing your alumina hafnia differently if you have different porosities. Or do you know if that's a factor?
So it's known with atomic layer deposition that as much as ALD can coat really complex structures, you are limited in how complex based on the precursor materials you use. So we believe that it won't be a problem with the aluminum doped, the aluminum precursor or the hafnia precursor in coating our metal foams completely, even if you're dealing with a really dense metal foam, and that's just the nature of the precursors, but that wouldn't be true with all ALD growths. With all the precursor materials you could choose to pick from.
So now a question from Karen Durham. Is this stronger than ion batteries?
Hi, Karen. Thanks for coming out. So again, it's just a matter of what parameter you're looking at. So you can see that in terms of power density, definitely. In terms of energy density, definitely not.
So can you speak to the reliability of your samples?
Yeah, so when we talk about reliability, we think of how many times can you cycle this sample before it breaks. And so we've done some characterization on that front, and we can cycle our capacitors up to 10 to the 7th times at 40% of the breakdown field with no change in behavior. We've also done a study where we just land on electrode 1 and do all the measurements, land on electrode 2, do all the measurements, and start comparing where and when our samples break down, just from sample A to sample B to sample C. And we have shown with a Weibull distribution that we actually have really reliable samples overall. It's not just we got the magic sample for these numbers. If you test a lot of our samples, you still get these results. So they're very reliable.
It's impressive. And so what would your initial application be for these devices and phones?
Yeah, so they most easily compare with commercially available tantalum capacitors. And so you can see them fitting in a lot of spaces that those do, which is like DC-DC converters in notepads and tablets and things like that. So we're thinking more about in components and electronic circuits, or in the circuit for a defibrillator, things like that.
Well, those are all very important. So I think those are all the questions we have. So
Great.
Thank you for that wonderful talk. And make sure to tune in next week, and we'll be having Professor Kevin M. Daniels from the University of Maryland presenting on the carbon scaffold, building next generation sensors and electronics on epitaxial graphene. But thank you, Alexis.
Thank you for having me.